Okay, we are continuing the previous day problem where we were asked to find out the flow behavior and consistency coefficients. We have done n value and that was coming a negative, but I asked that please check whether it is correct or not. Hopefully you have seen whether we have done any calculation mistake or not. But let us now find out the other one, that is k, right. So, to get k, we start with that we had psi is equals to 0.75 plus 0.25 divided by n, right, if we see it correctly, right. So, I think if we look at here, n was coming 1.58. So, let us take that. So, it is 0.75 plus 0.25 by 1.58, right. So, this means this is coming equal to 0.75 plus 0.25 divided by 1.58. So, it is equal to 0.908, that is 0.91, right. So, psi has come to be 0.91. Now, let us look the other. Gamma at the wall was 4 times V average over R into psi, right. This was 4 times V average, second case we got 1.99 and R was 0.004 and psi was 0.91, right. So, this comes roughly equal to, not roughly, this comes equal to 4 times 1.99 divided by 0.004 is equal to into 0.91, 1810.9, that means roughly 1811, right. So, if this is true, then we can say from the relation mu apparent is equals to k gamma w at n minus 1, right. This is, we can write that therefore, k is equals to mu apparent over gamma at wall to the power n minus 1, right. Now, mu apparent we got 6.7 in one case, in the other case we got, just a minute, let us look into mu apparent, we got 1.005 10 to the minus 2. So 1.005 10 to the power minus 2, and gamma at the wall we found out 1811. Of course, we are taking 1.58 as n minus 1, right. So this gives equal to 1.005 into 10 to the power minus 2 is equal to this divided by 1811 to the power 1.58 minus 1 1.29 10 to the power minus 4, 1.295, that is 1.3 into 10 to the power minus 4 Pascal second to the power n, right. So whatever it be, you try and find out as much as you can. So to wind up the classes, let us say that we have done right from the Navier-Stokes equation, or we have started even earlier from equation of continuity, right, and the equation of continuity we have done for both Cartesian coordinate as well as for the cylindrical coordinate, right. We have developed that. We have also done this other one, that is for equation of motion. Equation of motion we have done for Cartesian coordinate, and we have done number of problems, if you remember, right. If you remember, we have done number of problems for that. For example, in some of the problems we have said the viscosities how can be found out. We have also said that how Navier-Stokes can be applied for different cases, right. How the Navier-Stokes equations can be applied for different cases. We have also done, along with flow through pipe, we have derived with the shell momentum balance, and we have said that this shell momentum balance, that Hagen-Paiseli's equation, that also can be derived from the equation of continuity and equation of motion, that is the Navier-Stokes equation. So from the Navier-Stokes equation also we have developed how we arrived at the Hagen-Paiseli's equation. Only the thing what is required to apply the Navier-Stokes equations are, you have to be careful about the problems which is given or which are given. Those problems, if you look at carefully and see which are the terms they are not there, or which are the terms they will go out, right? And exactly the expression which will retain, which will stay, that you have to tell, right? So, if you can identify those parameters, then you can solve Navier-Stokes equations for any problem. That is known as the mother of the all equations in fluid flow, right? Based on that, subsequently all these others are developed. So, if you can utilize that, it is very, very good that as and when whatever problems you come across, use Navier-Stokes equation and find the solutions. Those different terms in the Navier-Stokes equation, be it in Cartesian coordinate, be it in cylindrical coordinate, or be it in spherical coordinate, whatever it be, all the three we have given, out of which Cartesian and Cartesian we have done, and cylindrical and polar we have given, because development of that would take long time. So we did not want to find concentrate on that. So if you can get problems and solve them with the help of the Navier-Stokes, then I think you will understand more and more about this and its application. So in the pipe flow we have done, and then we introduced that fanning friction factor, right? Normally, if the friction factor is not there, then for any pipe flow or fluid flowing through pipe, that should not have pressure drop high. But the pressure drop is high, that indicates that it is not only the fluid but also something else that is being pulled by the, or that is being pulled and that is pulling rather, and the fluid is losing the pressure from one end to other end, to reach from one end to other end, right? And this is taken care of by the fanning friction factor, right? Then we also have seen, which is very, very useful also in most of the cases, as we have shown in tubular heat exchanger, the flow is similar, that flow through annular pipe, right? So in the annulus, how the flow is taking place, if you come across, if you can do that, then you can also understand the flow through the tubular heat exchanger, right? We have also said that for homogenization of fat globules, what do you do? You pass the fat globules or milk typically through the valve, and this is called homogenization valve. And that valve has a very, very small orifice or small hole or small gap through which when milk is flowing, that the fat globule gets disintegrated from higher size to lower size, and in that the fluid which is flowing to that undergoes a severe pressure drop, and the fat globules are sheared and brought down into smaller particle size or smaller fat globule sizes, right? Generally it is around 2 micron, which we normally every day we come across the milk is around that 2 micron. So there also that flow through the pipe, we have seen how it is useful, and now flow through the slit, how it is useful typically for homogenization of milk or similar things, right? We also have seen or done some of the problems where we have done with both flow through the pipes and flow through the slits for both Newtonian fluids and for non-Newtonian fluids. Now, for Newtonian fluids, we are normally use, because most of the cases we handle are Newtonian fluids. In the, this is I am referring with respect to the food material. I am not saying all food materials are Newtonian. Many are, some are also non-Newtonian, but we have also developed that what is the flow behavior or flow characteristics for both non-Newtonian as well as Newtonian fluid. Newtonian fluid we have done earlier first, and then we have done for non-Newtonian fluid, right? So this way, if we can find out, or we have found out this way, that what is the flow characteristics for non-Newtonian fluids when it is flowing through slits, right? If the fluid is non-Newtonian, what is the flow behavior or velocity profile or the stress profile, how it is coming up, that we have shown, isn't it? Yes. Then we have also seen that is very important when this is typically when you are doing a refrigeration or cooling. That time you are passing high pressure, that condenser pressure is very high, that is going through some valve that is called the expansion valve, and during that expansion valve from the high pressure condenser, when it goes to the evaporator, there is a throttling, right? And this throttling, that behavior, the flow characteristics also we have done for flow through very small orifices or nozzles, right? Flow through the nozzles, what is the discharge, what is the velocity, those we have done. Also we have done what is the maximum discharge and what is the maximum velocity we can attain, and that maximum velocity and maximum output or flow rate, right, velocity or maximum discharge, that can be attained when we have also seen the pressure ratio that becomes to be critical, and the value of the pressure ratio is 0.528. If you remember that inlet to outlet, right, inlet to outlet, that pressure ratio, outlet to inlet, that pressure ratio, when it is 0.528, then it becomes critical, or if it is inlet to outlet, then it is 1.894 to my memory, right? So that is what we have also shown, that how good it is, and also we have shown that when the flow rate or when the flow is under critical condition, then it gains it attains the velocity of sound, right? That is why we can hear the sound when the fluid velocity is equal to the velocity of sound, we can hear it, right? That is what we have given, we have said that it is the sonic velocity or supersonic velocity or subsonic velocity. So when it is sonic or supersonic velocity or subsonic velocity, then if it is sonic, then we can hear, but subsonic or supersonic we cannot hear, right? And I gave perhaps the example of the aeroplane, typically fighter planes, right? When it attains that, when it changes from subsonic to sonic or supersonic, that time there is a huge sound which we have come across because of the location of our institute. We get this very often, right? So fighter planes are going above, and when it is changing from one, that is super to sub, or super to sonic and then to sub, or vice versa, that time we get lot of this kind of booming in the air, right? This we have done. We have also given some example of the flow through the nozzle. For example, that siren is one of the best example of this, that during the war or during any other, even in the industrial areas where this siren is normally being used to intimate the workers or people working in that company that the time of leaving or time of journeying are already arrived, right? So that indicates, that kind of the siren or sound indicates that the time is either over, or the old people will go out and the new people will come in for working, right, after the definite shift. Usually in the industry there are 3 shifts, 8-hour one shift, and normally it is 6, 10 and 6 2 and 10 in the evening, 6 o'clock in the morning, 2 in the afternoon, and 10 in the evening. So if it is like that, then during those period we hear those kind of sounds. This is one of the greatest example of the sonic velocity or flow of fluids through slits or very fine orifice, right, or nozzle, orifice or nozzle, right? We have also done the flow characteristics for pack bed. Pack bed is very useful because in many cases there are packing materials through which they may have to be sterilized, or they have to be pasteurized, or some heat treatment, or even cold, some cooling is required. In those cases, these pack beds are very effective. One of the example of the pack bed is that if the bed is utilized for heating or cooling, and in that case, if it is heating or cooling, whatever be the situation, when we are using pack bed, that may also lead to the fluidization, right? And fluidization, we have said that it is nothing but when corresponding to a velocity of the fluid, the particles do attain certain velocity, right, where it is called the onset of fluidization, right? So onset of fluidization, once it is there, after that you get that the particles starts moving and they start dancing, or they start floating into the environment. So this is what usually we have seen in many cases, particularly we gave the example of peas when they are getting frozen. Before that, they are, in many cases, they are subjected to such kind of freezers where it is the fluidized, right? Fluidization takes place, right? And in that fluidization, the particles do float, and they do take the this fluid that gives sufficient pressure, sufficient thrust from the below, and the particle starts floating or it starts moving. That condition we call it to be fluidized condition, right? So under fluidization, the advantage is that we get the exchange of the either heat or cold very that the heat transfer goes up, because you are increasing the available surface area. And when you are fluidizing, the height of the bed, that is also increasing. That is only because that when it was compact, and it increases the void space in the bed, or void volume in the bed, that is increased. So whenever you are doing that, you have to be careful that how much fluidization you want. Obviously, the higher fluidization you want, the more. I had also shown you one animated scene, animated situation where the particles were really there were very turbulence in that. It may not be required to go for the turbulence, but it is required that the particles are fluidized or coming in contact in all the way, all the surface of the particles are coming in contact with the fluid, right? You may heat, you may cool, that is a different case, but whatever be the process you are utilizing, that the fluid has to come in contact with the particles from all its sides. That is the advantage of fluidization, right? So like that, we have given lot many examples, lot many problems also we have solved. Hopefully you also have taken care of, you have also done lot many problem solution at your home or in your place. So if you have problems, if you have not understood or any queries, you are welcome to come to us through the portal given, and I am very thankful that all of you have all of you have registered for this course. And the course, if you would like, and if you want that many of your other friends who have not registered, they should also undergo, then you can request the authorities to recirculate or initiate or telecast it or repost it, so that refloat the course, so that many others who have not come across can also undergo the same, right? I am thankful. So thank you all. So with that, you try your best to do the best of the course, whatever you have learned, utilize them. So thank you all.